In the last lecture, I introduced to you the concept of function. I told you basically the calculus is a study of operations that you can perform on different functions. I told you a function is nothing but it is a mapping from one set to another set. The mapping is done from A set to B set. Then the first set is known as the domain of the function and the second set is known as the range. So we also discussed about domain and range of certain function. Then I told you the type of function, that is one-to-one function or many-to-one function. Okay. Then we saw even and the odd function and the periodic and aperiodic functions. Periodic functions were those which repeat themselves after a certain point. And even functions were those which were symmetric about y-axis. Odd functions were those which were symmetric in first and the third quadrant or second and the fourth quadrant. Then we looked at some of the functions like modulus function, which returned the magnitude of a number. Then we looked at GIF function, which returned an integer that is less than the given value but it is highest among all the integers. The opposite of that was LIF, that is least integer. It gives me an integer value which is higher than the given number but least of all such integers. Then we saw fractional part function, which was x minus GIF of x. And at last we saw the signum function. Okay. In this lecture we will be starting with the concepts of calculus. We will see what kind of operations can you perform on function. So first of all, let us discuss the symmetry when you are drawing a curve of any function. Usually there are two types of symmetry: about y-axis and about y is equal to x line. Now if the function is symmetric about y-axis, then function of minus x comma y should be same as function of x comma y. That is the basic criterion of even function, that you can replace x by minus x. Is it fine? Because if it is symmetric about y-axis, it means the function is even. Example, y is equal to x square minus 4. In that case, if you take minus of x square, it will be x square minus 4. So it is not affected. If you want to judge the symmetry about y is equal to x line, then if you replace x and y in the function, then the function should remain same. Is it fine? That is if the positions of x and y are replaced. Suppose I give you a function x square plus y square plus xy equal to c. Then if you replace y and x, it will be y square plus x square plus yx, which will again be c. So it is constant, then it is symmetric about y is equal to x line. Now why we do not study the symmetry about x-axis? Because suppose a function is symmetric about x-axis like this, then for one input we will have two values of output, which basically violates the definition of a function. What did I tell you in the definition? I told you a function is the one mapping which maps any input to a unique output. That is, for a single input we can only have single output. We cannot have multiple outputs. That is, one to many relationship is not possible. So that is the basic definition of a function. And that is the basic difference between a relation and a function. Basically, in a relation between two sets, you can have one to many relationship, but in a function you can never have one to many relationship. Always for a unique input you will get a unique output. Now let us discuss about the limit of a function. Now what is meant by limit? Basically, when you are hovering around near to certain point and you are determining the function value, that is known as the limit. Suppose fx is defined in neighborhood of a point a, which belongs to real number. What is meant by neighborhood? Suppose on the real axis this is my point A. So if you define fx in the nearby region to A, on the real axis, that will be known as my neighborhood. Okay, is it fine? Then fx is said to tend to limit L as x tends to a. Okay, this arrow sign represents tends, that is, it is approximately equal to. Is it fine? It is not exactly equal, but it will be going towards L as x will be going towards a. If it is going towards L, I will say mod of fx minus L will be less than epsilon if x minus a is less than delta. Or the formal definition of a limit would be for each epsilon such that mod fx minus L less than epsilon, there exists a delta such that mod of x minus a is less than delta. That is, if I fix a region, that is, if I fix a limit epsilon, that your function should be within the epsilon range of the limit L, then you can easily find a delta such that x lies in the delta range of a. That is, suppose I give you a curve. Okay. Suppose this is a certain curve, and if I am hovering around this point, then if I give you the function must lie within this range, then you can say that x must lie within this range. So this range will be the delta range and this range will be the epsilon range. Okay. So first I will fix the range on the function value or on the y-axis. Then I will say if there exists a range in the x-axis for which that range in the y-axis is possible, then we will say the limit exists and we will represent it like this, limiting x tending to a, fx is equal to L. That is, as x will go to a, the function limit will be equal to L. Now when we are talking about limit, usually we define two type of limit. Since there are two ways in which you can reach a, either you can reach a from the left or you can reach a from the right. That is, if a is here on the number line, either you can go to a from here or you can come from the right hand direction. If you go from the left hand side, it is known as left hand limit. Okay. On the real axis, this direction is for increasing values and this direction is for decreasing values. That is, if I move towards right, then I will be proceeding from 1 to 2, then 3, then 4. So I will be increasing the values. That means on left of a, you will have a value, let us say x is less than a. On right of a, you will have a value greater than a. So that is why when we are talking about left hand limit, I will say limiting x tending to a minus fx. A minus means the value which is less than a or it is slightly less than a. So I will say that a minus is equal to a minus h, where h tends to 0. Since you want to hover around the point a, so you will take a point less than a, but the distance between them should be tending to 0. Because if I take a point a minus h, then that will lie here. But I want this distance to be negligible, that is why h should tend to 0. So this can also be written as limiting h tending to 0 f of a minus h. Is it fine? Similarly, when we talk about right hand limit, then basically I will be approaching x from the right hand side. That is, I will be hovering around a point which is greater than a. So I will say limiting x tending to a plus fx. Again, a plus I will write as a plus h. So it will be written as limiting h tending to 0 f of a plus h. Now we will say the limit of a function will exist if these both limits are equal. That is, if limit h tending to 0 f of a minus h is equal to limit h tending to 0 f of a plus h, then the limit is said to exist. Otherwise we will say the limit of a function does not exist. Is it fine? So limit will exist only when left and the right hand limit is equal. Now let me show you where the limit will not exist. Let me show you an example. Many of you might have come across it already. If I take function of x as unit step, okay, electrical and electronics engineers specially go through this function. So the graph of unit step function is something like this. It is 0 just before 0 and just after 0 it is 1. Now if I want to find out the limiting x tending to 0 fx, then as you see, if you are lying to the left of 0, what is the value? 0. So left hand limit will come out to be 0. If you are to the right of this point, then you can see the function value is 1. So right hand limit is 1. As you can see, left hand and the right hand limits are unequal. So we will say limit does not exist. Is it fine? In such cases, the limit is said to not exist. For such kind of function, when you have different values on the right and the immediate right and the immediate left of the certain point. Now sometimes it may happen that you will get an expression where you cannot determine a limit, or the expression may be undefined. What kind of those expressions? If it is 0 by 0 or 0 into infinity, infinity upon infinity, okay, infinity minus infinity, 0 raised to the power 0, 1 raised to the power infinity, infinity raised to the power 0. These all expressions cannot be determined. That is, you cannot assign a numerical value to such kind of cases. If you have such kind of cases, then we use L'Hopital rule, that is this rule. So what does it say? If you have a form 0 by 0 or infinity by infinity, that is, let me say I have a limit like limiting x tending to a fx upon gx, where limiting x tending to a fx is equal to, let us say 0, limiting x tending to a gx is also 0. In that case, it will become 0 by 0 case. So this limit will also be equal to limiting x tending to a f dash x by g dash x. Okay. And still, if you are getting a form of 0 by 0 or infinity by infinity, you will differentiate it again, both the numerator and denominator, and you will continue to do so until you get a final expression or until you get a finite value. That is, you must get an expression whose numerical value can be determined. Remember, whenever you are seeing a rational function, that is the ratio of two functions, then you can divide the limit between those functions. That is, limit x tending to a fx by gx can also be written as limiting x tending to a fx by limiting x tending to a gx. Similarly, you can divide or you can separate the limit in addition, subtraction processes, okay, whenever you have such kind of cases. Now this is only about the two forms, that is 0 by 0 or infinity by infinity. What happens when we discuss the rest of the forms? So the objective when we are dealing with rest of the forms will be to derive those forms into this form, that is 0 by 0 or infinity by infinity. Now suppose if we have a limit like limiting x tending to 0 fx gx, where limiting x tending to 0 fx will be 0, let us say, limiting x tending to 0 gx will be infinity. In that case, you are dealing with the expression that is 0 multiplied by infinity. Okay. So what I will do is I will define a new function phi x, which will be 1 by gx. So limiting x tending to 0 or x tending to some other number phi x will be equal to 1 upon limiting x tending to 0 gx. So 1 by infinity will be 0. So I can write as fx into gx is basically equal to fx upon phi x. Now as I know limiting x tending to 0 fx is 0, limiting x tending to 0 phi x is 0, so it is a 0 by 0 form on which I can apply L'Hopital rule in order to calculate this limit. Is it fine? So that is how you can convert this function also into the indeterminate form that we saw earlier. The next indeterminate form is 0 raised to the power infinity or infinity raised to the power 0. So in the power expression, let me say the limit is something like this. Y is equal to limit x tending to 0 fx raised to the power gx, where limiting x tending to 0 fx can be 1 or 0 or infinity. Limiting x tending to 0 gx will be 0 or infinity. In that case, what you do is you take the log. So log of fx raised to the power gx would be gx log of fx. Okay. Now if gx tends to infinity, then it will be, what you can do is you can take phi x is equal to 1 by gx. Then this form will become 0 by 0, or it will become infinity by infinity. So what you need to do is you just have to take the log in order to calculate log of y, then again take antilog in order to derive y. So there are three cases. If you are getting 0 by 0 or infinity by infinity, you can directly apply L'Hopital rule. If you are getting 0 into infinity or infinity into 0, what you will do? You will define one function as a reciprocal of another function in order to get a 0 by 0 or infinity by infinity form. And if you are getting 1 raised to the power infinity, 0 raised to the power infinity, then you will take the log and convert it to again a 0 by 0 or infinity by infinity form. That is, for all sort of indeterminate form, you will always try to apply the L'Hopital rule in whatever way it is possible. Now let me show you some of the limits that you can directly use when asked in an examination. The first is limiting x tending to a x raised to the power n minus a raised to the power n over x minus a. As you can see, it is actually 0 by 0 form. So what you will do? You will apply L'Hopital rule. So you will take the derivative. So it will be limiting x tending to a. The derivative of the numerator will be nx n minus 1. Derivative of denominator is 1. So it will be n a raised to the power n minus 1. Similarly, limiting x tending to 0 e raised to the power mx minus 1 by x. Again it is a 0 by 0 form. So you will apply the same rule, you will get the value m. Then limiting x tending to 0 a raised to the power x minus 1 over x. Again it is a 0 by 0 form, because if you raise a to the power 0, it will be 1, 1 minus 1 will be 0, and denominator is already 0. So it becomes log e base a. Then limit x tending to 0 1 plus ax raised to the power x. So it becomes e raised to the power a. This limit has been derived by taking the log and then antilog. Some more limits. Limiting x tending to infinity 1 plus a by x raised to the power x, it is again e raised to the power a. Okay. Actually this should be 1 by x here, because if you are raising to the power infinity, okay, then only you can derive this limit. Then the next would be limiting x tending to 0 sin x by x or you can have 10x by x. It will come out to be 1. Okay. Again, you can apply L'Hopital rule here, as both numerator and denominator are tending to 0. So it is a 0 by 0 form. So derivative of sin x will be cos x. Derivative of denominator is 1. So it will be cos x. Cos of 0 is 1. Then similarly, if we extend this rule, limiting x tending to 0, sin of mx by x, it will come out to be m. How you can derive this? Again by L'Hopital rule, or the other way around is, you can multiply and divide it by m, so that you will get m into 1. Then limiting x tending to infinity, sin x by x. As we know, sin x is a bounded function, that is, it always oscillates between -1 and 1, whereas x is unbounded, it can go from 0 to infinity. So their ratio will come out to be 0, because even sine of infinity cannot go beyond 1. Then limit x tending to 0, a raised to the power x plus b raised to the power x by 2 will come out to be under root ab. That is geometric mean of both the values. The next limit is limiting x tending to 0, cos x plus a sin bx raised to the power 1 by x. It will come out to be e raised to the power ab. Then the last is limiting x tending to 0, 1 minus cos ax by x square. This will come out to be a square by 2. Okay. Here also you can see it is just the, what is this? This is 0 by 0 form, because cos of 0 is 1 and denominator is also 0. So you can take derivative. So it will be a sin ax over 2x. Again it is 0 by 0. Take one more derivative. It will be a square cos ax by 2. Now if you keep x equal to 0, it will be 1. So it will be a square by 2. So most of these limits have been derived from the L'Hopital rule. So that is very important that you remember such a rule. Is it fine? So let us see a problem based on this. Here I need to find the limiting x tending to 0, 1 minus cos 3x by x sin 3x. So here if you see 1 minus cos 3x, limit x tending to 0. As x tends to 0, cosine function tends to 1. So 1 minus cosine will tend to 0. What about limiting x tending to 0? X sin 3x. As x tends to 0, sine as well as x tend to 0. So it will also tend to 0. So it is basically 0 by 0 model. So I have to apply L'Hopital rule. If you differentiate the numerator and denominator, it will be limiting x tending to 0. Derivative of numerator will be, it will be plus, minus will be plus 3 sin 3x, and the derivative of denominator will be 3x cos 3x plus sin 3x. Even if you see now, the derivative, the numerator as well as denominator will go to 0 as x tends to 0. That means you need to apply L'Hopital rule again. So differentiate it once again. 9 sin 3x divided by minus 9x sin 3x plus 3 cos 3x plus 3 cos 3x. Now as you can see, though the numerator will tend to 0 as x tends to 0, but it will be 9 cos 3x. So numerator will tend to 9 as x tends to 0, and the denominator will tend to 6, because it will be 3 plus 3 6. This will be 0. So the limit will come out to be how much? The limit will come out to be 9 over 6. That is, it will be 3 by 2. Is it fine? So that is how you calculate the limit using the L'Hopital rule. Moving forward, it is asking the limiting x tending to a GIF of x does not exist when a is. I showed you the graph of GIF in the previous lecture. It was something like this. Now if you see an integer point, let us say we see 1. To the left of this it will be 0, to the right of this it will be 1. So it is discontinuous, or sorry, we will say the limit does not exist at x equal to 1. So if you say a is an integer, then what is the limit x tending to a minus 1 GIF of x? If it is a minus, that is just less than a, the limit will be a minus 1. What if it is greater than a? Since GIF yields the integer which is less than the given value but highest, so it will be a. Here I am assuming a is a integer. Now as you can see, the left hand limit is not equal to right hand limit, which means the limit does not exist. Is it fine? So basically, what I mean to say, if you have a number, let us say 2. Now if I ask you to find the GIF of 1.9, it will be 1. If I ask you to find the GIF of 2.1, it will be 2. That is, the left hand and the right hand limit are entirely different, hence the limit will not exist. So that is the basic rule to check the existence of limit. Now let us talk about another function or another property, that is the continuity. Continuity means the function continuously changes. Okay? There is no break in the graph of a function. Break in the sense the graph will be smooth, it will not break anywhere. Now how you will say that it does not break or it is continuous? For that thing we have a condition limiting x tending to a f x should be equal to f of a. That is, the limit as you tend towards a should be equal to the function value at the same point. That means limiting x tending to a minus fx should be equal to limiting x tending to a plus fx should be equal to f of a. Now if I give you again a function like unit step, as you can see, it changes suddenly here. So it is discontinuous. That is what I mean to say. A continuous function does not have a sudden change, or it flows smoothly. Like if you see a sinusoidal function, it is like this. There is no sudden change anywhere. Okay. So this function will be my continuous function. So first of all, for continuity of a function, the limit should exist at that point, and then the limit must be equal to the function value at the same point. Let me show you this by an example. We need to check the continuity of a function whose definition is that it is x square minus 4 over x minus 2 when x is not equal to 2, and it is 0 when x equal to 2. We need to check the continuity at x equal to 2. So what I will do is limiting x tending to 2, x square minus 4 over x minus 2. So now first of all I will check here whether or not the limit exists. For that, if I calculate left hand limit, it will be limiting h tending to 0 f of 2 minus h, that is limiting h tending to 0 2 minus h square minus 4 over 2 minus h minus 2, that is limiting h tending to 0 4 plus h square minus 4h, that is h square minus 4h over minus h. So if you divide it by minus h, it will be limiting h tending to 0 4 minus h, which will be 4. So the left hand limit comes out to be 4. Okay. Now if you calculate right hand limit, how much will it be? Limiting h tending to 0 f of 2 plus h. So it will be limiting h tending to 0 2 plus h square minus 4 over 2 plus h minus So if you expand the expression in the numerator, it will be 4 plus h square plus 4h. That is h square plus 4h over h. That is limiting h tending to 0, h plus 4, which is equal to 4. Now as you can see, left and the right hand limits are equal. That means the limit exists, but the function value at 2 is 0. So limit is not equal to f of 2. Okay, that means function is discontinuous. Is it fine? Both the left and the right hand limits must be equal, as well as they will be equal to the function value. Then the function will be set to continuous. Let me summarize what we have covered in this lecture. First, I told you about the symmetry property. That is, a curve is symmetric about y axis if f of minus x comma y is equal to f of x comma y. It is symmetric about y is equal to x line in case f x comma y is equal to f y comma x. Then we learnt about limit of a function. I told you there are two limits, left hand limit and the right hand limit, and once both are equal, then the limit is said to exist. Then we studied about L'Hopital rule, which is used to calculate the limit for the indeterminate form, that is 0 by 0 or infinity by infinity. We saw how you can reduce other forms to the standard form in order to apply this rule. Then we saw some of the standard limits which we can easily derive using L'Hopital rule. Then we saw the concept of continuity, that the limit must exist and it must be equal to the function value at that point. So in the next lecture, what we will do is, we will see a few problems based on the limit and continuity, so you know how to apply these conditions.